In this video, we're going to discuss how to solve exponential equations. So exponential equations are going to be different from other types of equations we've seen because now the variable is the exponent. So it looks like an exponential function is in the equation now. And so we're going to obviously need to solve these differently than the other types of equations we've looked at. Sometimes when we look at the two sides of the equation, we see that they can be written with the same base, and that's the case here. The left side is written with a base of 2, and we can also write the right side with a base of 2 because 32 is 2 to the 5th. And we know that our exponential function is 1 to 1. We've discussed that before. The function y equals 2 to the x looks like this, and it passes the horizontal line test. So it's 1 to 1 and has an inverse, which we've discussed previously. But let's go back to what it means to be 1 to 1. It means that each y value comes from only one x value. Each output comes from only one input. So the outputs in the function y equals 2 to the x is what you get from raising 2 to a power. So this value, 32, can only come from raising 2 to a specific power. There is no other number we could raise 2 to and still get 32. So what that means is, if we look at this, that means x has to be 5. There's no other option. You can't take 2 to the 5th and get 32 and take 2 to some other number and also get 32 because it's a 1-to-1 function. So we must have then that x equals 5 just by comparing the exponents there. So here's another example where we can do that. The left side is written with a base of 2. We can write 8 as 2 cubed. And since these two expressions are equal and they both have a base of 2, that means the exponents must be equal because 2 to the x is a 1-to-1 function. So we say, all right, 2x minus 1 has to equal 3 then, and then we can just solve that for x by adding 1 and dividing by 2. Sometimes it's a little less obvious what base we need to use when rewriting both sides. For example, here we have 1 over 8 and we have 16. First thing I'm going to do on the left here is think of this as 1/8 to the negative 1 to the x, because if we have an exponent raised to another exponent, we multiply those. Negative 1 times x is negative x. The reason I'm doing that is to make the left side a little bit easier to look at, because we can take 1 over 8, raise it to the negative 1 first, and that just becomes 8. It's the reciprocal of 1/8. So really the left side here is just 8 to the x. Now we can't write 16 with a base of 8. We can't take 8 to a power and get 16. But we can find a base that can be raised to 2 different powers to get 8 and 16, right? So 2, getting ahead of myself, 2 cubed is 8. That's where I got the 3 from. So we can write 8 as 2 cubed. We had 8 to the x, so just replacing 8 with 2 cubed, still raised to the x. And similarly, we can write 16 as 2 to the 4th. And so we just replace the 16 with 2 to the 4th, and then 16 had an exponent already. So again, we can multiply exponents here. 3 times x, 4 times 2x plus 5. We can distribute in the 4 there. And so once again, we have two expressions with the same base. They're equal, so the exponents must be equal. and then we can use that information to solve for x. Now, it won't always be possible to write both sides with the same base, so in that case we're going to need a different strategy to solve exponential equations. And to kind of explain how we're going to do that, I want to go back to some equations we've solved before. So for example, if we wanted to solve an equation like this, x cubed equals 27, if you think about what you would need to do to each side to get x by itself, you would take the cube root of each side. And the reason you're doing that is because if you cube root an expression that has an exponent of 3, those are going to undo each other and you're just left with x. Similarly, if you have a cube root and you want to undo that, you're going to cube each side. Cube the cube root, they undo each other, you just get x. The reason we do that is because the functions y equals x cubed and y equals cube root of x are inverses of each other. Those are inverse functions, which we've discussed previously. That means that when you compose them, when you put one inside the other, they undo each other, and you're just left with whatever's inside there, in this case x. So that same strategy is what we're going to do when we need to solve an exponential equation, and we can't rewrite both sides the way we were just doing. The inverse function of b to the x is the function log base b of x. So we're going to apply the inverse function to both sides if we can't do the method that we just did before. So for example, here we have 5 to the x. We want to get that x out of that exponential function. So to undo what's being done there, we're going to apply the inverse function of 5 to the x, which is log base 5 of x. So we're going to take log base 5 of both sides. We have to do the same thing to both sides of the equation, or else we've changed the equation and it doesn't have the same solutions anymore. So we're going to take log base 5 of both sides, and the reason we do that is because now on the left we have a composition of inverse functions. They're going to undo each other and we're just going to be left with the exponent. So the exact solution is this, x equals log base 5 of 16. That number is not an integer, so if we want the exact solution we would leave it like this, kind of like how if we're solving an equation and we get a solution of square root of 3, right? The exact solution we just write with the radicals, square root of 3, and then if we need a decimal approximation we can put it in the calculator. Now if you need the approximation and your calculator does other bases of logs, then you can use that. If it doesn't, if you have like a scientific calculator, for example, or an older graphing calculator, it might only do two bases. It might only do natural log or log base 10. And so if that's the case, and you know you're going to need the approximation, what you could do when solving this is take the log of both sides with a different base, one that your calculator does. So for example, if your calculator only does a couple logs and one is natural log, you could take natural log of both sides of the equation, and we don't quite have the same effect going on the left side there. We don't have inverse functions because they have different bases, but we can use a property that we've discussed previously where we can put the exponent out front of the natural log of 5. And so then we have x times natural log of 5 equals natural log of 16. And so to solve for x, we can just divide by natural log of 5. And so this is another way to write the same exact solution. These are equal by our change of base formula, right? And then then this is helpful if your calculator doesn't do log base 5, you can punch in natural log of 16 over natural log of 5 to get the approximation, which is about 1.72. So as I solve these, I'm going to keep using the base that's in the problem as much as possible, but just know that if you need an approximation at the end and your calculator doesn't do any base you want, you can do it this way as well. All right, if the exponential part's not by itself, we need to get it by itself first so that then we can proceed with what we were just doing. Because, for example, here, the exponent of x is not on the 2. The 2 is not being raised to the x. 10 is being raised to the x, and then that result is being multiplied by 2. So to undo that multiplication, we can just divide by 2, and then we'll have the 10 to the x by itself. And then we can take log of both sides. I'm going to use our common log, log base 10, so that it's the inverse function of what we have on the left side there. Don't forget to take the log of both sides. Whatever we do to one side of an equation, we have to do to the other. And then since I used log base 10, I have inverse functions on the left side, and we just get x. So x equals log base 10 of 4 is the exact solution. And if you need an approximation, you can type that in your calculator, and it's about 0.602. Here's another example where we need to get the exponential part by itself first. So the e to the exponent, that is what we want to isolate. So we're going to need to add 3. And then we also need to divide by 2. So it's kind of like solving just plain old linear equations at first. You're trying to get something by itself by adding, subtracting, dividing to get that by itself. And then now that we have the exponential thing by itself, we can take log of both sides. I'm going to use natural log since we have base e there. So take natural log of both sides. We have inverse functions, one inside the other on the left side, and so those undo each other, and we're just left with the exponent. And then to get x by itself, we just need to subtract 1 from both sides. And then be careful how you write this. I would probably write it as negative 1 plus natural log of 23, although you can write it as natural log of 23 minus 1, but it is not natural log of 22 because we're subtracting 1 after we take log of a number. We're not going inside the log and subtracting 1 from 23. So this is going to be about 2.14. Okay, here we have two different bases. So important thing to note, again, we have to do exactly the same thing to both sides. So when we take log of both sides, we have to use the same base. For example, if you were solving an equation, you would not take the square root of one side and the cube root of another, right? Because you haven't done the same thing to both sides. Same thing here. So it doesn't matter which base we use. I'm going to use base 2, then at least one side will have that nice inverse function property. So I'm going to take log base 2 of both sides. Doesn't matter what base you use. So if you have a calculator that won't do log base 2, you might choose to use natural log here on both sides. That's okay. We'll get the same answer in the end, even though it'll look different depending on what log we use to write it. Since I used log base 2, though, I have inverse functions on the left side, and I'm just left with 3x plus 1. On the other side, I don't have inverse functions because I have different bases. I have base 2 on the log and base 3 on the exponential part. But, like I showed you earlier, we can use that exponent property, put the exponent out front of log base 2 of 3. Now keep in mind for the rest of this problem, log base 2 of 3 is just a number. We used a lot of characters to write it, but that's just some number. So we've got a number outside of parentheses. Let's distribute that in. And keep in mind our goal, right? What are we trying to do? We're trying to solve for x. So on the left we have 3x plus 1, and on the left we have a number minus x times a number. That's what we have. So just like solving any other equation, if you're solving for x, you want to get the terms with x together on one side, and the terms that don't have x, the terms that are just numbers, on the other side. So I'm going to add x log base 2 of 3 to both sides so that my x terms are both on the left, and at the same time I'm also going to subtract 1 so that I don't have that constant term on the left with my x terms. Now we don't have any like terms here. I mean, we have two terms here with an x, but we can't combine them because we don't have an easy way to add 3 and log base 2 of 3 because we're trying to keep everything exact. So just leave those terms separate. And same thing over here. Can't combine those because we want to keep the log expressions exact. Alright, so we have our terms with x on one side, our constant terms, our terms without x on the other side. We still need to solve for x, and we've got x showing up in two different terms here. So what we're going to do is we're going to factor an x out. Because we're trying to get this to say x equals, so we don't want to see two x's floating around there. And now that we have x times something, we can solve for x by dividing, because x times the stuff in parentheses. We're going to undo that by dividing. And so we just have x equals negative 1 plus 4 times log base 2 of 3 over 3 plus log base 2 of 3. There are different ways to write the solution depending on how you solved the equation. So I mentioned earlier you could have used natural log, you could have used log base 3, so obviously your answer is going to look different, but they're equal to the exact same number. Also, even if you used log base 2 like I did, but you put the x terms on the right and the constant terms on the left, it's going to look a little different, but it is the same value. And you can type this in your calculator carefully. You're going to need parentheses around the numerator and denominator if you do that. And it comes out to about 1.16. We can't simplify this at all, by the way, because there's addition here and here, so we can't like divide anything out because it's separated by addition, not multiplication. Okay, this one looks a little bit different because we've got an e to the x, and we have an e to the 2x, and we have a constant term. So we've got three terms here. We're going to treat this kind of like a quadratic, and we've done some substitution problems before where we substitute u for something and it ends up looking like a quadratic. In this case, if we substitute u for e to the x, then u squared is e to the x squared because we're saying u equals e to the x. So u squared is e to the x squared, which is e to the 2x because you multiply the exponents. So we can replace e to the 2x with u squared, and we can replace e to the x with u, and then we have a quadratic equation to solve. So this is going to factor as u minus 7 times u plus 5. So we end up with u equals 7 and u equals negative 5. And then we just need to go back and solve for x. So u was equal to e to the x. And we can solve this by taking the natural log of both sides. So we get a solution of x equals natural log of 7, which is about 1.95. Now you may notice something funny about this part. E to the x equals negative 5. We didn't get negative outputs from our exponential functions, right? If it was just a basic number raised to a function, number raised to the x. E is 2 point something, so e is a positive number. You can't take a positive number, raise it to something, and get a negative number. So this doesn't make any sense. But let's say you didn't recognize that. Let's say you didn't realize that e to the x can't come out to be negative. You might say, okay, well, I'm going to take natural log of both sides here. And then hopefully this would clue you in at this point. Wait a second, I can't take log of a negative number. That's undefined. We can't take log of a negative for precisely the same reason that this statement doesn't make sense, right? Because our exponential function can't have a negative output, its inverse can't have a negative input. And if you type natural log of negative 5 in your calculator, you'll get an error. So all that means is this equation we started with only has one solution. So remember that when you end your problem by solving a quadratic, it looks like it might have two solutions or more, because most quadratics have two solutions, but your original equation might not have two solutions, and that's what we saw here. All right, an application of all this, suppose you invest $500 at an annual interest rate of 6.75% compounded quarterly. We've discussed compound interest formulas previously. This is our principal. Our rate is going to be 0.0675 as a decimal, and we're compounding 4 times per year. And then this formula gives us the amount after t years. So if we substitute 500 for p, 0.0675 for r, and 4 for n, t is what we're solving for because it says how long will it take your money to double. So we're finding t. What about a? Did they give us a? Well, we want to know how long it takes for the money to double. We started with 500, so at the end of this amount of time, we're going to have twice that, so 1,000. So this is an exponential equation. It's more involved than some of the other ones we've done, but we're solving for a variable. It's in the exponent. So we want to start by getting the base to the exponent part by itself. So we're going to divide by 500 so that we get that out of the way. And while we're at it, I'm going to go ahead and figure out what this 1 plus this fraction is. We do want to keep that exact. So if it doesn't come out exact, I would leave it as is. But in this case, it comes out exact if I write the whole decimal down. So it's not a base we're used to seeing, but it is the same type of equation we've seen, base to an exponent, the variables in the exponent. So we need to take log of both sides. And in this case, we're probably not interested in the exact answer, right? We don't want to answer the question how long with a log expression. We want just a decimal. So I'm just going to use natural log on both sides here. Mostly because I don't want to write that whole thing as a subscript. Since I didn't choose the same base I don't have inverse functions, but I'm going to write the 4t out front with that exponent property that we've used before. And now we have 4 times t times another number. So to solve for t, we're going to divide both sides by the other numbers. Now you can divide by one of those numbers at a time, or if you want to do it all at once, like what I'm writing here, just make sure that you put that denominator in parentheses. Otherwise, if you type all that in your calculator at once without the parentheses, your calculator is going to think that the natural log is in the numerator. And so we get about 10.4 years.